In section 8.4, we're going to discuss some tests of claim of a hypothesis or a population mean. So our hypothesis will be about a population mean. Now, typically speaking, in all our hypothesis tests, there's going to be some assumptions. Now, in this particular case, the assumptions are pretty light. They're going to be that x is distributed normally, or we have a sample size greater than 30, and that we can at least calculate what sigma is, or what S is. Now, if S is distributed normally, then one other thing we need to know is sigma. And that is sigma, the standard deviation, is known. That's really an unlikely situation. I don't see that you would not know what the population mean is if you know what the population standard deviation is. If you did actually know both, then you could use the front side of your handout. That is a test for a population mean with an unknown, actually this should be known. Yeah, this should be known, not unknown. A known standard deviation. It turns into a z-test. But like I said, that's rather rare. I can't really see too much circumstances by which that would be true. So let's stick with something that's not so rare. And that is, we're testing a claim about a hypothesized mean, and we don't know what sigma is. That's more typical. So that's going to result in a t-test. Now, as we go through our hypothesis test in this section and the next section, they're all going to fall into what I hope gets to be a familiar pattern so that you guys can kind of catch a rhythm in these next two chapters, chapters 8 and 9. You're going to start out all your hypothesis tests by stating the null and alternative hypothesis. Significance level is going to be given to you. And then these two steps, I'm hoping to replace these with some technology. As opposed to, taking out your t-tables and finding these critical areas, then computing your test statistic by hand, man, here's what we're going to do. We're going to input the data or summary statistics. So that's going to be step 3. And step 4 is going to get replaced by find the p-value. So the p-value is going to get a lot of work done for us. It's going to mean that we don't need to find the critical areas of this distribution anymore. And it also means we're just going to look to our computer output to give us the p-value of this test statistic. We won't even have to compute that. That one will be given to us. Once we have the p-value, you're going to decide if you reject or fail to reject. So here's your decision time. Reject H0 or fail to reject. Be careful that you don't state somehow or another that we're proving that H0 is true. We never prove anything in the stat course. In particular, we're not going to prove that H0 is true. Last but not least, state your conclusion in words, and we've got a handout on that. I definitely refer to the handout as you state your conclusion in words. So let's do a couple problems then. Get used to hypothesis test. So we'll start out with problem number 12. The weights of discarded plastics from a sample of households is listed in dataset 23, Appendix B. The summary statistics are this: that we had 62 samples, average weight of 1.911 pounds, standard deviation of 1.065 pounds. Use a 5% significance level to test a claim that the mean weight of discarded plastics from the population of households is greater than 1.8 pounds. So let's key in on this first. We're going to test the claim that the mean weight of discarded plastics is greater than 1.8 pounds. So that's the original claim that we're going to be testing. What parameters should I write down as part of my null and alternative hypothesis? Mu, sigma, or p? Mu. Good. Because we're testing a claim about a population mean. So step 1. My original claim is mu is greater than 1.8. Is that going to be the null or alternative hypothesis? Alternative, good. So that's HA. Yongshan, what should I put in for HO? Yongshan? Human? Sabrina? Good. So it's just going to be the opposite. So if you're one, or you could be one or the other, but not both. So HO always has to contain the possibility of equality. So that's our step 1. State the null and alternative hypothesis. There's probably like 4 points wrapped up in here. A point for getting the parameter correctly, and then the signs correctly, etc. Step 2, we wanted to perform this test at a 5% significance level. So alpha is 0.05. I'm just double checking that that's the case. Yeah, here we go. Alpha is 0.05. Step 3 is where we input our data. So again, let's turn to StatDisk. Let's go to StatDisk. Where do you think we're going to go in this case? Where have we gone several times? Analysis. Good. So go to analysis. This time, instead of a confidence interval, we want to go down to hypothesis testing. What kind of hypothesis are we testing here? A mean for one sample. So analysis, hypothesis testing, mean one sample. And let's select that. And we're going to use our summary statistics. We'll do another one next where we use the data, but this one let's use the summary statistics. So the summary statistics were a sample size of 62. The mean of that sample size was 1.911, and the standard deviation of that sample size was 1.065. Now before you hit the evaluate button, we need to decide what the alternative hypothesis is. The mean is not equal to the claimed mean, or is it greater than or less than 1, 2, or 3? What's the form of our HA? 2. Our mean is greater than the claim mean. That's what we're testing. And to kind of go back and take a look at that, let's take a look right here. Our mean is greater than the 1.8. So that's where we're getting our decision to go for 2 on this little chart. Say again?
Should they change the claim mean? That's 100.
Oh yeah, there we go. This should be 1.8. All right, I think things are looking good. So let's click evaluate. So step 2 was to enter our data. Or step 3 was to enter our data. What do I need here at step 4? The p-value. So in this case, the p-value is 0.2075. In step 5, you got to decide whether or not you're going to reject or accept. So take a minute and decide what you think. Are we going to accept or reject the null hypothesis? So here's your alpha, here's your p-value. Charles, what do you think? What are we going to do with our hypothesis? Or are we going to accept or reject? Want some help on that one? Bottom? Yeah. So fail to reject. Fail to reject H naught. Remember, if P is low, H naught must go. So if this is lower than alpha, then we can get rid of it. Sabrina? Yes. So the sample mean, so there was several summary statistics given to us. The sample mean was 1.911. 11. Sample standard deviation was 1.065. And the sample size was 62. So these are your summary statistics. So if you have the summary statistics, you can enter them in that way. StatDisk also allows you to use data as well. So the next one we'll do it with data. Okay, just so we have the comparison there. All right, the last thing is that we need to do is state our conclusion in words. So our original claim, does our original claim include the possibility of equality? No, it doesn't. So let's see where that branches us to. Original claim does not contain the possibility of equality. Did we reject our original claim, or did we reject H naught? No. So you're down here. So this is the wording of your solution, of your conclusion. There is not sufficient evidence, not sufficient sample evidence to support the claim that the mean weight of trash is greater than 1.8 pounds. So step 6. There is not sufficient sample evidence to support the claim that the mean weight of trash is greater than 1.8 pounds. So keep that hypothesis testing wording of the conclusion sheet handy. You're going to go to it a lot. Are we okay with the wording of the conclusion here? Now, what's nice is that our program StatDisk gives us a lot here, but it gives us a little bit more. That's actually really helpful. It gives us a confidence interval. So here's a 90% confidence interval for the true population parameter. Now, it's saying that we can be 90% confident that the true population mean is somewhere in this interval between 1.685 and 2.136. Is this confident interval consistent with our conclusion that we failed to reject? Do they match? What number does this confidence interval contain that's really important, that makes these two things match? Yeah, 1.8. 1.8 is part of this confidence interval. It wouldn't make sense to say, oh, we reject the claim that, the mean is at most 1.8 when 1.8 is there. 1.8, we think, is a possibility for the true population mean. So we're not going to conclude that it's greater than 1.8. That would be inconsistent with our confidence interval. There's actually 3 different ways you can do your hypothesis test. One is to do it with a confidence interval like we just did. One is to do it with a p-value, and the other one is with test statistics. If you wanted to do this with test statistics, here's what it would look like. You'd be setting up a critical region. So that critical region is going to put, whatever percent of the area in the tail that you want. That percentage is going to be alpha. So in this case, it'd be someplace about 1.7. Actually, right here, 1.67. And when you calculate your test statistic, if it falls in this critical region, then you'd reject. That's kind of a little bit of an old school approach. It worked great when not everyone had a graphing calculator or StatDisk or some other programs available, but now that we do, hey, let's just do it with a p-value approach. And this p-value is consistent with our conclusion based on the confidence interval, and if you actually graphed it and did it with a test statistic and a critical region. All right, unless there's some follow-up, we're going to do another one just like this. This time, we'll do it based on some data. Okay, so let's take a look at problem number, I think I want to do 16. In Dataset 15 in Appendix B, 48 different departure delay times for American Airlines flight from New York JFK to Los Angeles. Negative departure delay times correspond to flights that departed early. The mean of 48 times is 10.5 minutes. The standard deviation is 30.8 minutes. Actually, you know what? This isn't going to require us to use the data, is it? No. We can use our summary statistics. 20? Okay, yeah, let's do that one then. All right, thanks, Dan. Age of race car drivers. Listed below are the ages and years of randomly selected race car drivers based on data reported in USA Today. Use a 5% significance level to test the claim that the mean age of all race car drivers is greater than 30 years. All right, so let's enter some data into StatDisk. Maybe let's set up the null and alternative hypothesis and then go enter some data into StatDisk. So we want to use the 5% significance level to test a claim that the mean age of all race car drivers is greater than 30 years. So try and set up your HO and HA. I'll do likewise over here. Okay. Max, what do you think we'll set up for HO and HA? Okay, good. So if the alternative is that the mean is greater than 30, then the null has to mean that the mu is less than or equal to 30. Cool, thank you. Now, just for convenience for later on, let's note that this is your original claim. That's the one we're testing. And we note that so that we can look later and figure out the wording of our conclusion. So that's step one. Step two, we're going to perform this test at the alpha is 0.05 significance level, very typical significance level. Step three is step four. Step three is to enter our data. So let me write down the data. Actually, you know what? We'll do it this way. There's the data. We're going to put that in a column of stat disk. So you guys are pretty good at catching my typos. I'd appreciate somebody double checking me on this one. I want to make sure that my data matches yours. So we got a couple values of 32. So 32 twice, and then 33 twice, then 41, then 29, 38, 32, 33, oops, 33, 33 again. Oh, it's a 23. Oh, man. I'm still wet behind the ears. Jeez. 27, 45, 52, 29, and 25. Okay, so we've got our data entered. We want to form a hypothesis test. So let's go up to analysis, down to hypothesis testing, and then over to mean one sample. Let's choose the alternative hypothesis. Kind of like the last one, we're claiming that the population in mean is greater than something. In this case, it's going to be greater than 30. 5% significance level. Change the claim mean. That's 30. Don't enter the population standard deviation, even if you knew it. This would result in a z-test. We don't want to do a z-test. That's that case of sigma is known that I said it's not realistic. So let's go down to use data. Our data is in column 1, so we should be able to click evaluate. I think we've got everything we need here. And the computer is going to do a lot of work for you. It's going to calculate the mean, the standard deviation, the t-scores, the critical value, the p-value. Just does it all. So we can concentrate on the last step, which is the conclusion. Step 4, our p-value. 0.0453. So that's definitely something to get out of this thing. P-value is 0.0453. Take a moment and make your decision. Are you going to reject or fail to reject? Feel free to double check your decision with your neighbor. But you don't want to round it when you're comparing it. Just use the p-value without rounding it. So, what's our consensus opinion? Reject or fail to reject? Reject. Good job. So, reject H naught. If alpha was 0.01, would we reject H naught? No. If alpha was 0.01, you wouldn't. So it's nice that you're giving somebody the p-value when you're doing these kind of test results. So that way they can kind of make their own determination. And it depends on what the consequences are of a type 1 error. I mean, is it a really, really bad thing to make a type 1 error here? If it is, then you want to make your alpha really, really small. All right. I don't think the consequences here are that dire, so let's move on to step 6. Fail to reject. I guess I would stick to reject H naught or fail to reject H naught. Those are the ones I would stick to here. Yeah, I appreciate what you're saying, but I like to go back and refer to H naught in this decision. All right, so again, try and figure out where we're going to go here based on the original claim and our decision, etc. Try and work your way through the chart. Does the original claim contain the possibility of equality? Yes or no? Did you reject? Yes or no? So you should be able to find your way to one of these 4 possibilities here. Try and word your conclusion. Practice wording it. Make sure that yours matches mine, or at least is pretty close. So I'll give you a minute to work on that. But because we're not really spending as much time with the actual number crunching, then I'm going to want a little bit more from you in terms of the conclusion. I want you to be very careful about the conclusion here. Someone want to give it a shot? State their conclusion for yourself and the world. Max?
Sample data support the claim that the mean age of all drivers is greater than 30 years.
Perfect. Now, the author seems to like to go back to the idea about the sample data support the claim sometimes, and I kind of like that. I mean, these are conclusions based on data. They're not empirically proved facts to the extent that a math proof is, but we're pretty confident in our conclusions. So the sample data support the claim that the mean age of race car drivers is greater than 30. Let's look at the confidence interval and see if the confidence interval matches this conclusion. So go back to StatDisk. Our confidence interval was 30.11 is less than mu is less than 37.09. Does this match our conclusion of rejecting H naught? Does this match our conclusion that basically we think that the mean age is greater than 30? Why? What is it about this confidence interval that matches this conclusion? Yeah. It doesn't even include 30, right? This confidence interval is strictly greater than 30. Wherever this population parameter is, it doesn't include 30. So it's greater than 30. Thanks, Liam. All right. Your confidence interval and your decision should match. If they don't, take a look at things. They should match. Okay. Let's do another one. Or are you comfortable with this? You want to do one more? We can do 26? Okay. All right. Let's take a break then. I'll give you a few problems and homework. Try 9 through 19, 25, and 27.